Hello, my name is Sultan, and this is Group 9's video presentation for the Signals and Systems assignment. My group members are Hanif, Yahya, Alifuddin, and Amirul Zarif. This project explores how energy is stored and dissipated in RLC circuits, which consist of resistors, inductors, and capacitors. We analyze capacitor charging in series and parallel configurations using MATLAB simulations and with various input signals, step, sine, and pulse. Key performance aspects such as rise time, settling time, and overshoot are examined along with frequency responses using Laplace and Fourier transforms. The effects of resistance and inductance on damping, efficiency, and stability are also evaluated to determine the better performing configuration.
For our methodology, we started by deriving transfer functions for both RLC circuits using Laplace transforms. Then, we simulated capacitor voltage in MATLAB using TF and LSIM with a custom GUI to input R, L, and C values. Finally, we analyzed rise time, overshoot, and frequency content using FFT to evaluate how R and L affect circuit behavior.
For the series RLC circuit, we applied KVL and transformed the differential equation into the Laplace domain. The resulting transfer function, where the output is the capacitor voltage, is H of C equals to 1 over SRC plus LC S squared plus 1. This second-order function allows us to analyze key characteristics like natural frequency and damping ratio. It also serves as the foundation for simulating how the circuit responds to different types of input signals in the time and frequency domains. For the parallel RLC circuit, we used KCL and followed a similar process. After applying Laplace transforms and simplifying, we derived the transfer function as h of s equals to SL over SL over R plus 1 plus S squared LC. Unlike the series case, this configuration behaves more like a bandstop filter. The structure of this transfer function helps us understand why parallel circuits exhibit smoother, more stable responses, especially at their resonant frequencies.
Hello, Doctor. I'm Muhammad Isan Hanif. So let's moving on to task 2, where we generate the three types of input signals using MATLAB step, sine, and pulse. The step signals delayed at 5 milliseconds simulate a sudden voltage application. It helps test the transient response, especially rise time or an overshoot. Next, with the sine wave at 50 Hz representing the AC power signals, it's useful for analyzing the circuit's steady state and resonance behavior. Lastly, the pulse signal or square wave challenges the system's ability to handle fast transition, great for observing ringing and distortion. All the signals are scaled between plus minus 1 and sampled over zero point 0.1 seconds to ensure high resolution analysis. For the step input, we observe clear difference between series and parallel RLC circuit. The series RLC response shows visible oscillation and a peak voltage of around 1.46 volts with a rise time of 5.8 milliseconds and high overshoot of nearly 47%. The FFT confirmed this with a wide frequency spread indicating strong resonance. In contrast, the parallel RLC response with no overshoot, a much faster rise time of just 0.001 seconds and smooth settling. Its FFT shows narrower frequency content, meaning better energy damping. For the sine wave, the series RLC tracks in the input closely with slight attenuation, behaving like a bandpass filter. The parallel circuit attenuates the sine wave more, showing bandstop behavior by suppressing signals near resonance. Moving on to the pulse response, the series circuit shows clear ringing at each transition, and its FFT reveals strong high-frequency activity. On the other hand, the parallel RLC gives a much cleaner output with smooth edges and better suppression of harmonics. This makes it better for signal smoothing. To summarize task 3, the series RLC excels in speed and resonance, making it ideal for fast switching application. Meanwhile, the parallel RLC provides better stability, damping, and clean transition, which are great for filtering or noise sensitivity systems. In task 4, we varied R and L values to observe their effect on damping. We calculated the LC and RC coefficient from the transfer function. LC influenced the natural frequency, while the RC controlled the damping. Lower R and L values gave faster but oscillatory response. Higher values resulted in more damping and smoother but slower voltage transitions. The series RLC, as R and L increase, both of the coefficient increase, leading to more damping and longer rise time. This matches our earlier step response observations. And in the parallel RLC, each of the R and L combinations shift the pole location to damping ratio. The result clearly shows a transition from underdamped to nearly critical damp behavior, which is visible in the simulation graphs. And that's all of my part. Now I'll pass it to the next presenter, Yahya. Thank you.
Hello, my name is Yahya, and I will continue to task 5, damping behavior in RLC circuits. We investigated how changing the values of resistance R and inductance L affects the damping behavior of both series and parallel RLC circuits. The damping ratio, lambda, is a key parameter that tells us whether a system is underdamped, critically damped, or overdamped. In a series RLC circuit, increasing resistance increases lambda, making the system more stable but slower. However, in a parallel RLC circuit, it's the opposite. Increasing resistance actually reduces damping and causes more ringing. We simulated 5 different cases by varying R and L and observed the voltage response to a step input. And the results showed that with low R and L values, the circuit responds quickly but with significant oscillations. At higher values, the response becomes slower but much more stable.
Okay, my name is Alifuddin. So I will explain about task 6, frequency and time domain analysis using Laplace and Fourier transform. So there is two input, which is step input and sun input. For the step input, energy mostly in low frequency, and sun input dominant frequency at 34 Hz. So this apply to both series and parallel RLC circuit. So for the Laplace domain interpretation for the series RLC, for the poles location we use this equation and substitute the value of R, L, and C, and we use the quadratic formula to get the poles location. For the damping analysis, we use the second order formula, which we get natural frequency is 213.2 radian per second, and the damping ratio is 0.234, which show underdamped because it is less than 1. And for the parallel RLC, the post location, we use this formula, substitute the value of RLC, and we get two value of poles using quadratic formula, which both is real and negative. For the damping analysis, we use the same formula, and we get natural frequency is 213.2 radius per second, and the damping ratio is 1.066, which is overdamped because it is more than 1. For MATLAB code for extract time domain characteristic, we use this shown code for the series, and result displaying time domain characteristic is as shown. And this is for parallel RLC. We use this code and result displaying time domain characteristic as shown below. And for task 7, comparative analysis, it is series versus parallel RLC charging. So the parameter we use is charging speed, rise time, overshoot, settling time, oscillation, and energy dissipation. So you can see this is the comparison between series and parallel RLC.
For task 8, we simulated both series and parallel RLC circuits using a step input to observe and analyze the capacitor voltage response over time. The simulations were carried out using MATLAB with fixed values for resistance, inductance, and capacitance. The parameters used are 10 ohm of resistor, 0.1 Henry for inductor, and 220 microfarad for capacitor. This simulation allows us to extract time domain features like rise time and settling time using step info in MATLAB and observe the frequency components through FFT and Bode plots. Like you guys can see, same goes to series RLC circuit and parallel circuit. We compile the following parameters from the output waveforms, which is rise time, settling, overshoot, and steady state value of the capacitor voltage. Firstly, for series RLC circuit, the capacitor charges faster with a shorter rise time but shows some overshoot and oscillations, especially if underdamped. This is typically due to the resonance behavior when L and C interact with low resistance. Meanwhile, in the parallel RLC circuit, It shows more stability, but the charging is a bit slower. It also has minimal overshoot and settles more quickly without oscillating much. In terms of steady-state voltage, both configurations eventually reach the input voltage, showing they are functionally correct in steady state. Now, I'll be presenting the comparative discussion between the series and parallel RLC circuits based on 4 key aspects. First, in terms of charging speed, the series RLC circuit charges the capacitor faster. This is because all the current flows through a single path, allowing energy to be delivered to the capacitor more quickly. In contrast, in the parallel configuration, currents get divided, which results in a slower voltage build-up across the capacitor. The second one is the damping behavior and stability. The parallel RLC circuit is more stable and better damped. It tends to settle more smoothly with minimal overshoot, while the series RLC circuit may oscillate if the damping is low, especially when resistance is small. The next one is the energy efficiency. The series RLC circuit is more efficient overall. It has only one path for energy dissipation, which reduces losses. On the other hand, the parallel RLC allows energy to dissipate through multiple paths, leading to lower overall efficiency. Lastly, for filtering and frequency response, the series RLC acts as a band pass filter, allowing signal near its resonant frequency to pass. Meanwhile, the parallel RLC acts as a band stop or notch filter, blocking signals near resonance and passing others. So the choice between the two depends on whether we want to select or reject a frequency band. In summary, series RLC is better for faster charging and efficiency, while parallel RLC provides better damping and stability. Filtering performance depends on the application needed.